trimino, all right, one way to do that. And so we get the same thing happening, again, by the nature of the fact that we know what the sum of the roots are, the product of the roots, the sums of the pairs of the products of the roots. You know, that's what the roots do. So it satisfies the same recurrence. All right, so what are the impurities here? I want to once again show that the impure tilings sum to 0. So I'm going to say a tiling has an impurity. Any tile that has length 2 or 3, anything that's not a square, that's impure. A square that has a weight of Ri, or CRI, followed by any tile that has a weight that doesn't include Ri. Okay, so like they're incompatible. So for example, this would be impure because R2 is followed by something that doesn't have R2. These are impure just by the fact that they're dominoes and triminos. And this would be impure, right? R2 followed by negative R1, R3. If there had been an R2 in here, that would not be an impurity. Notice that these two hold hands with each other. Right? I can turn this into that. I can turn that into this. How do I know that this is going to turn into that? If it was my first impurity, if it had been preceded by all squares of weight R2, then this can only go into that, and that can only turn into that. And similarly here. This turns into that turns into that. So the non-initial impurities sum to 0.
Sorry, I have a question.
Yes?
You just said that any tile of length 2 or 3 is an impurity.
Yes.
But if the R2 there is replaced by an R1, you said that's not an impurity.
If
the R2
this here
is R1, if replace that R2 by R1,
then that would not, then this is going to turn into that. This impure situation would turn, suppose this was my first impurity, blue, 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 orange. First impurity, that becomes this. And if I were blue, 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 white, that's going to, I have to split that into a square domino, and the color of that square is blue. Okay, so it is reversible. All right? And if the initial impurities, they sum to 0 too. I mean, that's how we designed them. Whether a domino is in this orbit, this trio that sums to 0, or a trimino, or these other 3 sorts of arrangements, all of those weights sum to 0. So we get lucky. Well, it works again. So there are 3 pure tilings, just like before, all of one color, and so their total weight is that. Okay? So that's 3. Same argument works, really no new ideas in going into the kth order recurrences. Okay, so you just define the square weights and the domino weights exactly like I've been leading you to do. Similarly, the initial tiles have the same weights, just like we've seen before. Okay, and so let's now go on to the next step. What about repeated roots? Okay, we've got the distinct roots case. What about repeated roots? Well, like a second order recurrence would look like that. Okay, then if that's my characteristic polynomial, then we know that the solution looks like that. And if it's a repeated root of order k, then we know that the solution looks like that. And more generally, you know, it's just generally messy. All right. So, but we can do all of these combinatorially. Let me take the intermediate ground and do the case where I've got a single repeated root of order k. Same tiling model as before, but now I have to add some coins into the process. Okay? So imagine so here's the situation. I've got one root of order k. Let's call that root r. But let's pretend for a little while that they really are k distinct roots, r1 through rk. We'll treat them as different, even though numerically they're all equal to r. I'm going to give everything the same weights as we did before, except now I'm going to also add coins. So I'll slow down for a second to describe what the coin situation is. For given tiling, let m denote the largest index to appear anywhere on the tile. If m is the largest index that appears in the tiling, then you put m minus 1 distinct coins on various tiles of the tiling, and you're allowed to put more than one coin on a tile. The only restriction is the only tiles that are allowed to get coins are ones that had that biggest number, Rm, as a factor. The coins do not affect the weight of the tiling, they simply give us more tilings. Let's do an example, of course. So before I put coins, let's say this was my tiling. What's m? It's the largest index up there, that's 3. I see it here, I see it here, I see it there. So I have to put m minus 1, 2 distinct coins on the tile. All right, so I've got 3 places where the first coin could go. It could go here, here, or here. Let's say it goes there. And I've got another place for a different coin, different color. Okay, we put it there. There were 9 ways of doing that. All right? Here was what would m be in this situation? What's the biggest number index you can see there? 8, right? That's the biggest index. So I have to put 7 coins down. They're only allowed to go on these 2 tiles. Let's say we do it that way. Same impurities as before. I'm not going to change my impurity rule. Any tile of length greater than 1, any square of weight Ri or Cri, followed by any tile that doesn't use an Ri. So this is impure. All those things that were impure before are still impure. The only difference now is when I separate, when I go from here to here, where do the coins go? They go where they have to go. They have to stay on the tile that has the largest index. So that's what allows us to go back and forth. This initial impurities still sum to 0. What we saw before, the non-initial impurities still sum to 0. And so the punchline is, so the pure tilings, well, so all the impure tilings sum to 0, just like before. What are the pure tilings? Well, this one, where m is 1, and there are no coins on that, all blue. Well, with an index of 2, that means it has to have 1 coin on it somewhere, and I've got n choices for where that 1 coin goes. So the total weight of these is an n times a C2R2 to the n, and so on. And here I'll have n squared ways of placing the coins. Here I'll have n to the k minus 1 places to put the coins. Now what I didn't tell you though, I snuck something by you. All the beautiful combinatorics works, but why should that coined model actually satisfy the same recurrence? Kind of slid that one under the rug, right? Because we're low on time, let me say, it does satisfy the same recurrence. You can show using the very same types of arguments we've seen already that the total weight of all tilings that have any coins on the last tile, any coins at all, 1 or more, has a total weight of 0. So therefore, I really can reduce this to, what's the last tiling? It's either of weight A1, A2, AK. There's a little extra details that I'm shoving under the rug here, but it all works. So I think I've given the punchlines here. They satisfy the same recurrence. It's counting the pure tilings. And so I'll just leave it to say, in the most general situation, really no new ideas are needed. You just find the very first impurity, and everything works from there. So I think I'll stop here. Thank you very much. Two challenges.
Let's do a continuous analog. Look at a linear differential equations.
Continuous analog, okay.
Continuous
We will continue that investigation.
Combinatorial model to this. And the other one is the so-called Zeilberger algorithm.
The so-called
Zeilberger algorithm.
Oh, yes.
Inputs a binomial coefficient sum and outputs a recurrence,
Yes.
giving an ugly, awful computer-generated proofs.
Yeah.
It'd be nice to get a Benjamin-style combinatorial projective proof, at least to some of the more famous ones. For example, the sequence.
Okay. Thank you very much.